Hello everyone. So today lecture we see a beautiful application of group theory in the study of topological space. So the idea that if you have a topological space, then at every point, say you have a topological space X, this with the topology, let's say tau, and if we take a point, let's say P, and then at this point we can attach a group. So that group we will call the fundamental group of the space X at the point P. So you can think like this, that you take your space X and this side you take all the group. So this side all groups. So then our target here is to, in this actually lecture, that we will define a map from the X to the collection of all groups. So basically that we call the map F. So how it is defined? So F of, if we take any point P, then this we denoted by pi1 of X comma P, which is a group under some binary operation. In this lecture, we will see how to construct this map. Basically, for every point, we see how to attach a group at that point, or how to construct a group for the point P. So the idea here that this fundamental group idea is very important, because using the fundamental group of a space, we can distinguish that space from other space. So we'll see this theorem later, but first we will develop the fundamental group concept. So how to proceed this? That let's say suppose suppose we have a topological space. Suppose X comma tau is a topological space, and let's say P, we take a point from the space X. Now let's say define a loop at the point P. So let me put here the heading loop. So loop at the point P. So we'll define this. So any continuous function sigma from close interval 0, 1 to the space X, such that sigma 0 equals to sigma 1 equals to P, then so any continuous function such that this is called a loop, is called a loop in X at point P. So geometrically what happens, that you are taking a continuous map. So basically you have here close interval 0, 1. Now we have a continuous map sigma, such that the sigma 0 and sigma 1 are the point P. So this means if you look at the image of sigma, then sigma is a closed loop at this point. So that we called a loop in X at the point P. Okay. Now, how many loops are there at point P? There are infinitely many loops, right? So now we will use those loops to construct a group at the point P. So, and this is not easy one, because if you consider all the loop, then on the collection of all loop, what we have to define? We have to define a binary operation under which it will be a group. So how to proceed this way? That so let me consider the, so let us consider all collection of all loops at P in X by this notation. I denote it by L X comma P. So this is the collection of all loop in the space X at the point P. So now define the equivalence, let's say define a relation. So that is called the homotopy relation. So I am writing here the homotopy. So let me use the different colors. So we'll use here different colors. So basically the homotopy relation between two loops, you can say. So basically on this set collection of all loop at P, we are going to define a equivalence, a relation. Later we see that relation will be an equivalence relation. So how? So let sigma 1 and sigma 2 are any two loops in X at the point P. So that is, we took two elements, sigma 1, sigma 2 from the set L of X comma P. So defined a relation. So defined a relation tilde. I call it is, let's say, okay. So since it the name is related to homotopy, so triple equal, I say here H for homotopy relation by this way, that sigma 1 homotopy to sigma 2. If I will tell you the geometrical meaning of the homotopy of two loops. So to loops. So before do this, let me write here definition. Defined a relation, a homotopy this way, that if there exists a continuous map, let's say called I call it is, let's say you can call the H for homotopy. So H from close interval 0 1 cross close interval 0 1 to the space X, such that it has this property. So you can think your second interval is the time and the first interval for the domain of the sigma. Okay. So such that sigma of S at time 0, we are getting the loop sigma 1s for all S in between 0 1. Age of S comma 1 at the final time, or at the time t, we getting the loop sigma 2 S. So this is basically S less equal to 1. And also one more thing that I'm writing here. So age of 0 comma at any time and age of 1 comma at any time, this is nothing but the point P. So if we take two loop, let's say sigma 1 and sigma 2 in the space X at the point P, so we'll call sigma 1 homotopy to sigma 2 if there exists a continuous map from close interval 0 1 cross close interval 0 1 to X, such that at time 0 we are at sigma 1 loop and at time 1 we are at sigma 2 loop. And for every time the image of under homotopy we getting loop. So that basically this part telling us. So let me draw here image, then we understand properly. So here we have the space, let's say, and let me put it here that basically different color. So I'm putting here this here, and let's say because of the convenience I am putting here this color, and let's say this is here the time interval, this side this and this side this, and between I am putting here this color. Okay, so this is, you can think your 0 0, and this is 1 comma 0, this is 1 comma 1, and this is 0 comma 0 on the standard way. So this is nothing but, the whole set is nothing but 0 1 cross the set 0 1. So now we have a continuous map here, sigma from here to here we have a continuous map. So sorry, not sigma, H, and we have the point P here. Let's say this is the P point. Now for at time 0, So the image of this line basically, so image of this line is nothing but the sigma 1 loop, right? This loop, this is nothing but this, if you write, so this is nothing but age of s comma time 0, we know it is what, sigma 1 s. So this is this, and the red color basically sigma 2 loop here. So this is nothing but this loop is basically age of s comma 1. So this is sigma 2s, and in between this we are getting here that this is here something here. So this is at, let's say, at the time t. So this is 0 comma t. So this is nothing but that age of s comma t. So you can understand that suppose in the space x we have two loops, sigma 1 and sigma 2. We have sigma 1 and sigma 2, and then we say sigma 1 homotopy to sigma 2 if we can move from sigma 1 to sigma 2 in a continuous fashion. So one thing is clear, that if in between sigma 1 and sigma 2 some hole appear, then we cannot find a homotopy from sigma 1 to sigma 2. Basically the fundamental group actually what do here, that try to find out the hole in the topological space. If hole appear, then you will not get the trivial fundamental groups. That we will write properly here. Yeah, so this is clear. Now here it is the note to, it is to be note that the this relation. So this is checking part. So here note, this is an equivalence relation on the collection of all loop at the point P. Okay, so this is as an exercise. I leave it as an exercise. Otherwise, the it will take little more time. So, but I'm not want to spend time on here. So it is very trivial fact. Just check is reflexive, symmetric, and transitive. So now we move to the group structure. So now I'm denoting. So collection of all equivalent classes. So this is the equivalent class of all loops such that sigma is a loop in x at p. So we are considering here that two loops are equal in this set if they are homotopy, right? So now we are going to define a binary operation on this collection. So we will define a binary operation star on the set let's say pi 1 x comma p. So how we define? So let me take two loops. Let sigma 1 and sigma 2 are two loops in x at the point p. So now defined sigma 1 star sigma 2, one loop. How? So at time t, so it will be a map from closed interval 0 1 to the space x, and it will be a loop at p. So how I am defining? So defining this way, that sigma 1 of 2t if 0 less equal to t less equal to 1 over 2, and sigma 2 of 2t minus 1 if half less equal to t less equal to 1. So now this is clearly you can check that sigma 1 star sigma 2 is continuous by gluing lemma, and you can check sigma 1 star sigma 2 at time 0 equal to sigma 1 star sigma 2 at time 1, it is nothing but p. So what we are getting, that we are getting that sigma 1 star sigma 2 is still a loop in x at the point p. Now it is a theorem, you can check that if sigma 1 homotopy to tau 1, right, all are loop in x at p, and sigma 2 homotopy to tau 2, then what we get, sigma 1 star sigma 2, it will be homotopy to tau 1 star tau 2. So Here it will be tau 1 star tau 2. So I leave it at exercise. So very important. Why? Because later you will understand. Next page. So you understand the whole importance of this theorem. So I call the, yeah, this is a theorem. So now move to the next topics that so how define. So star from pi 1 x comma p cross pi 1 x comma p to pi 1 x comma p by, how defined it by, so sigma 1 class we take star sigma 2 is nothing but sigma 1 star sigma 2, this class. So then you know this is theorem. Then pi 1 x at p under star is a group. So this was our goal, that we wanted to define a group at the point P. So this is one way we define group. So now the idea basically here that all right. So let me, since I am claiming that this is group, so we need to think identity and the inverse of every element. So the identity will be what? Let me write it here. The identity element will be the CP, the constant loop class. Okay, this. So how CP defined? CP is a loop from closed interval 0, 1 to x. So CP at t is everything goes to the point P. Now what? How inverse defined? So if you take inverse, so let's say sigma is belongs to pi 1 x comma p. So sigma loop. So sigma is a map from where to where? Closed interval 0, 1 to x. Now define sigma bar from closed interval 1 comma x to this by define how sigma bar of s equal to nothing but sigma of 1 minus s. Just take the reverse of sigma. Okay, then you know sigma class inverse is nothing but sigma bar class. So this is the information about the identity and inverse. So what we get that if we take a topological space X and consider a point P, then we can define a group. We can define a group at that point, right? So what is the idea? Basically, take all loops. Then you say two loops are equivalent if there is a homotopy between those two loops. So then use and collection of all equivalent classes under this star. So sometimes this star called the product of two paths is a group. This is called the fundamental group. So now this group play a very important rules when we will actually compare two topological space, because if you know the fundamental group of two topological space, then you know there is an idea how to check they are homeomorphic or not. So before go to this, let me define the concept. So this is a theorem. So this is a nice theorem. So now the question, if you have a topological space X and if we take 2 points P and Q, can you find any relation? So can we find any relation between pi 1 x comma p and the fundamental group at P and pi 1 x comma q? This is very trivial question and necessary question, right? And the answer is yes. So I'm restricting here. If there exists a path, let's say I call it is, let's say, alpha from, so alpha, there is a path alpha in x between P and Q, then actually pi 1 x comma p isomorphic as a group to pi 2 x comma p. So this is isomorphic pi 2 x comma p. So how it is defined? So you can define, say, alpha, you consider a path. So it is a continuous map from here to here. So let's say you have a closed interval 0, 1 to here you have alpha. So path means this. So we defined a, so alpha head we define. This will give you a sigma x comma p to pi 2 of x comma p. How? By alpha head. Here we take a loop at p in x. So maybe the loop is this. So you can think this is the loop. And so you have a continuous map. Now close interval 0, 1 to here. Let's say it is sigma. We want to define a loop at q. So how to do? So you use the reverse path first. So this is definition alpha bar. So this is the reverse of alpha from here to here. Then move around sigma. Using sigma, you move around here. So then sigma, and then again you followed by alpha and reach the point q. So you started from here, that you started from, so this is the loop at point q. So is an isomorphism, of group. So one thing clear, that if a topological space is path connected, then it is enough. So if your topological space path connected, then if you know the fundamental group at a point, then at every point fundamental group is the same. Okay. So far from now, actually from now we will always consider a path connected space, because if you have two space different path component, then for every path component you will get different fundamental group. Yeah, right. So now the main theory. So here the theorem I am that was so far we get that if you take a topological space, of course path connected, that every point you have a fundamental group, right? So now now we compare two topological space, x comma tau. So not I'm considering at tau, so just writing here topological space. Let x and y are two topological space. X and y are two topological spaces, and f from x to y is a homeomorphism. Okay, here I am assuming that xy path connected. So homeomorphism. Then so we will not write the base point. Okay. So before write down, okay, let me write here. Then f star, I'll tell you what is f star. F star from pi 1 x comma p to pi 1 y comma f of p is an isomorphism. So this means if two space are homeomorphic, their fundamental group are isomorphic. So now, okay, let me tell you f star how defined. F is a continuous map from x to y, right? So let me choose here the base point, so then you understand properly. Here I am selecting the point P, and then here you can take y comma f of P. Now you can define here f star. It will be a map from pi 1 x comma p. How defined I'm writing? Pi 1 y comma f of p. How defined? F star of sigma loop if you take, then you just f composition sigma. So sigma was a loop in x, so it was a map basically. So here you have x, here you have y. So at p here f of p. Now you have a loop sigma here. Now here f is a continuous map. So take the composition. So basically you have close interval 0, 1 to here. You have a loop here. Take the composition. So then you getting a f composition sigma at f of p in y. So this. So f star defined. So any continuous map always induces a map f star between the fundamental group. Now it tells us that if xy are topological space and f is a homeomorphism from x to y, then f star, the induced map f star, is an isomorphism. So one thing clear that if you have two space and or let's say path connected, and fundamental group are not isomorphic, it is easy to check two group are isomorphic or not, because in the group you have lots of tools you can do. So especially for the finite group, you have Lagrange theory, Shalot's theory, all the thing, direct product, all the thing you can use, component wise you can think. But in the topological space, lots of things are difficult. So using group you can check two space are not homeomorphic. So let me tell you one thing that here. So example of fundamental group. So if you take Rn If you take Rn and any point P, it is path connected. So the fundamental group is basically trivial. So it contain only identity element, because any loop you can shrink to a point, because line segment homotopy you can use. It's trivial. Why? Because in R2, for example, R2, you take a loop at 0. You are considering R2. So now this loop is homotopy to the point 0, 0. Why? Because you can join by line homotopy. This to this to this, all the line homotopy will work here. This and up to this. So you can homotopy to C0, right? Any loop sigma, if you take sigma homotopy to C0. So any class is basically nothing but C0 class, right? So because of this homotopy. Now, if you take the circle, let's say we are taking the circle S1 at point, let's say P is, let's say 1, 0, you select. What is the fundamental group? It's now it is not a convex and not there, so therefore you cannot use the line homotopy. So there is a problem. So what will be the fundamental group? So I tell you, it is fundamental group is basically isomorphic to Z under plus. What is the proof? We need to develop the covering space concept, but just you remember that fundamental group of S1 is Z plus. Now see that all right. Now since S1 is fundamental group Z, so it's a clear that. So now if I give you a line here in R2, so what will be the fundamental group of this curve? Let's say C. So clearly this is homeomorphic to what? Just some interval a comma b, right? So the curve is homeomorphic to the interval a comma b. So the fundamental group of this is isomorphic to what? Fundamental group of the interval, and interval are convex. So basically pi 1 of a comma b. So this is trivial, right? So it is clear that fundamental group of this type of image, so pi 1 of this, is trivial. So the circle and these two curves are not homeomorphic. So without writing any map, just looking at the image, you can say two space are not homeomorphic. Just check the fundamental group. One more thing I will tell you, that if you take two space x and cross y, if you take and calculate the fundamental group at the point, let's say a comma b, it will be isomorphic to the fundamental group of x comma a cross fundamental group of y comma b. So the proof is what? Basically the proof will be, so this is theorem. So it is very useful. So for example, if you take the torus, right? So torus is this. Using this, we can calculate the fundamental group. So torus is like this. So torus means this, it is the subset of R3. Torus, you can think that. So torus I called T. So T is clearly is homeomorphic to the set S1 cross S1. Why? Because you take this circle, circle, and then this circle I called S1, and the black circle I call S1 also. For every, at every point you draw a circle like this. Every point you draw a circle, then you are making a torus. So this is nothing but S1 cross S1. So the let me write here torus is a, so this is, so say called, this is just T. So this is called just T. So torus T. So the fundamental group of torus at any point path connected, it's not isomorphic to what? Pi 1 of S1 cross S1. So this is isomorphic to pi 1 of S1 cross pi 1 of S1. So this is nothing but isomorphic to Z cross Z. So fundamental group of this space is Z cross Z. Basically, you can see, because the covering space is R2. So you can think that this is the covering space. So this is the fundamental domain. So R2 is the covering space for the torus, right? So that is the idea. But what I'm trying to tell you, that just if you know the this theorem and this theorem and then this theorem, then you can easily calculate fundamental group of some space. Okay, that's also how to calculate the fundamental group. So fundamental group is a useful tool to check some space are not homeomorphic. So now the question, how to calculate fundamental group of a arbitrary topological space. Now as we discuss, always a problem that you will think, so I'm writing here that. So so how to find find out fundamental group of any topological spaces. So this is big question. So there are lots of tools, the covering space, and also the Van Kampen theorem. There are lots of tools. You can think it. So you have a topological space. At every point you have loops. You say two loops are homotopy. If you can move from one loops to another loops, and all equivalent classes you can define a star that way. So, and then the question, if you have a space, then how to find fundamental group of the space? It's a very nice question, so you can think about. You can take a arbitrary space. For example, think about this. Take the open cylinder. So these two sides are open. So find the fundamental group of this. So try this one. Okay, and then check that the open cylinder basically is not homeomorphic to the torus. Just checking that are not homeomorphic. So try this one. So calculate the fundamental group of this, and the fundamental group. I can tell you this is, as I said, you can think S1 cross close interval 0, 1. So try this one. Okay, thank you. Good night. So see you in the next class again.